Hello guys, welcome to the third lesson of AP Calculus. Today we're going to learn about continuity. So when is a function continuous at x equals a? There must be three conditions that must be fulfilled. Limit as x approaches a of f of x must exist, f of a must be defined, and the limit must be equal to f of a. So let's take a look at an example here. We have a function x squared minus 4 at x equals 6. And we're trying to find out if the function is continuous at x equals 6. So we take the limit, and we plug in 6, and we get 32. We get f of 6, and we get 32. Since the limit and the f of 6 is equal to each other, then the function must be continuous at x equals 6. Let's take a look at this example. We're trying to find if this function is continuous at x equals 10. Oh, let's take the limit. We plug in 10 and we get 9 over 0. Does not exist. Oh, then let's try to find the other one. Let's see. F of 10 is equal to 10 minus 1, 10 squared minus 100, 9 over 0, undefined. Okay, since these two are both undefined, they're not going to be equal to each other. And since they are undefined, they do not exist. So the function is not continuous at x equals 10. So what are some types of discontinuities that we're going to see throughout AP Calculus? There are mainly three types. First one is called point or removable discontinuity. It says when limit as x approaches a of f of x is not equal to f of a. But an easier way to think about this type of discontinuity is whole, that we learned in pre-calculus or algebra 2. So it says in this example that there is a point discontinuity in x equals 3, and there is one point in the graph where it is undefined, and it can easily be filled with a point with a piecewise function saying 3 whatever value. And so to find this algebraically, as you learned in pre-calc, you'll expand it, and you'll find that you can cross one of x minus 3 on the numerator and x minus 3 in the denominator, and you'll get a point discontinuity at x equals 3. Another one is jump discontinuity. This type of discontinuity will be easily seen in piecewise functions. It's when limit as x approaches a from the right is not equal to a limit of x approaches a from the left. Let's look at this type of function. Oh, it's an x value function, and as it approaches 0, there is a jump discontinuity. Literally, the graph jumps to a different location. So that's another type. The last type is infinite discontinuity, or better known as vertical asymptote. This is when the limit as x approaches a from the left or from the right approaches infinity. As you look at it in this example over here, f of x is equal to 1 over x plus 3. Because when you plug in negative 3 into this equation, it becomes undefined. You know that there's going to be a discontinuity here. And since it's only in the denominator, it's going to be an infinite discontinuity, as you probably learned in algebra 2 or pre-calculus. So there is basically a discontinuity over here, a vertical discontinuity that looks like a wall that keeps the function from going across it. So, if a function is continuous on a closed interval, what three things are guaranteed? Well, if the function is continuous on the interval a to b, the function obtains the a minimum and a maximum value, which is called extreme value theorem. If m is a number such that f of a is less than or equal to m, f of a is greater than or less than or equal to m, but m is less than or equal to f of b, then there is at least one number c between a and b such that f of c is equal to m. This is called intermediate value theorem. If x sub 1 and x sub 2 are numbers between a and b, and if f of x sub 1 and f of x sub 2 have opposite signs, then there is at least one number c between x sub 1 and x sub 2 that f of c is equal to 0. Intermediate value theorem corollary. Let's take a look at examples on these theorems. So, if you look at it over here, f of x is equal to x squared plus 3x plus 2, interval negative 4, 5. We're trying to find a value m between negative 4 and 5 such that f of c is equal to 12. Let's see. We get a table, negative 4, f of x 6, 5, and 42. So there must be a value of c in between the values here. So we take a number, and c must be equal to 12. So we take the function and set it equal to 12, and we solve for the answer, and we get either negative 5 or 2, and it must be in between these intervals, so x must be equal to negative 2. And then we find a number c in between negative 4 and negative and 5 that satisfies the intermediate value theorem corollary. X, and that means that there must be a value 0 in between these two values, right? So we set the function equal to 0, and we solve for the answer, and we get x equals negative 2 or negative 1. We check the interval, and we find that both satisfies the intermediate value corollary. That is the end of our lesson today with continuity, and you'll probably be wondering that I didn't cover extreme value theorem. That is because it requires derivatives, so I really didn't want to get into it quite yet. Thank you for listening to me today, and have a wonderful day.